Halloldu değil mi?
Başlayabilirsiniz hocam.
Teşekkürler. Okay, sorry for the disturbance. Welcome to our morning session, all audience. Good morning, everyone. Actually, first of all, I would like to thank the organizing committee to invite me at this section. Actually, today we have 5 talks. First speaker for me, this is Uğur Tamer from Gazi University, Department of Analytical Chemistry. Today is my talk, Surface Enhanced Raman Spectroscopy-Based Quantitative Analysis in a Complex Matrix. Actually, first of all, I would like to introduce my group. Today, firstly, I'm going to concentrate on the Raman spectroscopy technique and our advantage or disadvantage using this technique. But in our group, we also make some study regarding the electrochemical sensing using some kind of different electrodes, such as this kind of paper electrodes. Actually, we are capable of producing a large amount of paper electrode using the wax printer and some printing techniques. And what we are doing in here is actually we are constructing this electrode, and we are trying to analyze the actually DNA or toxin and other target analysis in a complex matrix. And we also trying to construct some potentiometric sensor. Actually, these are all the kind of electrochemical sensor. But our aim is to make a simple electrode, okay, such as glucose sensor. Maybe you know there's a lot of commercial glucose sensor, but all this sensor is performance is not good. Maybe we can create a much more suitable sensor, and maybe we can use the wireless sensor. Because of this reason, we are going to construct some sensor system actually. Okay, we also make some image sensor in our group. For instance, in here, we are trying to analyze some glucose again in a tiers matrix. As you can see, using this paper surface substrate, you can change the color of the paper using some enzyme actually. Then image processor system can be used. But today I'm focused on our SARS-based technique actually. Why we are prefer this technique? This technique is very sensitive and very capable of detecting of some target spaces in a complex matrix. This is maybe you know this is the very delicate technique and label-free technique actually. But it is not easy actually. I am going to discuss the possibility of how to get the signal and how to interpret the signal from the complex matrix today. Okay, actually, we are continue to analyze the system in a complex matrix such as blood, serum, or saliva. As you see, these all the complex matrix, and it is difficult to analyze the target, for instance, bacteria, virus, and another toxin spaces. It is difficult to analyze this kind of analyte in a complex matrix. And SARS, or we call surface enhanced Raman psychedelic spectroscopy technique, is capable of detecting this target easily. But there's also some difficulties actually. In our groups, we made several application recently. Today, I'm going to give some example of this kind of application. For instance, we detected some toxin species in the blood or food samples. What kind of targets? For instance, ricin is a toxin, and or erythropoietin protein is a doping agent, or tau protein is a biomarker of Alzheimer's disease. And as you know, hepatitis B virus is also a very important target. And as you know, in these days, pandemic area is increasing, and everybody wants to use the technique to detect the COVID-19. But as you know, PCR is the top sensitive and cheaper, not exactly cheaper, but suitable techniques regarding the accuracy. Okay, but most of the people couldn't reach the PCR. Okay, because of this reason, we also think about the other serological techniques. But serological detection techniques such as ELISA or simple paper test is not sensitive and lack of accuracy actually. Because of this reason, PCR technique at the top in using actually in the clinical site. Most clinical guys prefer the PCR because of this reason. But we should look at the other technique also. How can we increase the accuracy of our system? Because of this reason, we are trying to use the other techniques also. Okay, but the one technique maybe is not enough. As you know, there's a lot of techniques, but you should check the other technique. Maybe you can use the hybrid techniques. Okay, one is colorimetric, one is fluorescence, or one is colorimetric, one is surface and Raman spectroscopy. If you combine these techniques, maybe you can increase your system's accuracy. Okay, actually today I'm going to give some basic term of the Raman spectroscopy also. As you know, this is the very delicate system actually. Why? Because only one photon is scattering inelastically. Maybe you are not familiar with the basic of the Raman spectroscopy. Briefly, I can explain the Raman spectroscopy as a scattering techniques. If a photon inelastically scatter from the molecules, okay, and the energy exchanged between photons and the vibration modes of molecules that give rise to photons with either lower energy, we call Stokes shift, and or higher energy, we call anti-Stokes Raman shift. Okay, polarizability also imported in here, but signal is very weak actually, because only one photon is scattering inelastically between the 1 million photons. Okay, because of this reason, you should increase the signal actually. How we can increase the signal? Actually, we are using some metallic substrate, and this metallic substrate control the light matter interaction, and the signal can be increased order of magnitude. Okay. Using this technique, you can analyze different kind of substrate actually. Okay, for instance, this is the latest application of the system. For instance, in here you are using the handheld Raman spectroscopy system. Maybe 20 years ago, equipment is very large, but now it is very small and carryable. They are also using in medicine. For instance, in here using the sound probe can be used in the brain imaging, actually. But there is some stability problem. Okay, but the laser technology and detector technology is developing, and the Raman spectroscopy technique popularity also increasing, especially during the last decade. Okay. In our group, actually, as I also mentioned, that we are trying to construct some optic sensor system using the some substrate. Why you are using the some substrate? Because we try to increase the Raman signal intensity. Because of this reason, with the collaboration of my colleague from the chemistry department, Gökhan Demirel, we constructed a gold or silver layer. Okay, if we made some gold on silver layer or copper layer on the substrate, you can increase the signal. Also, you can also decrease or diminish the fluorescence signal using the kind of metallic substrate. Okay, and I'm going to give some example of these applications. Actually, Raman spectra are very powerful techniques. As I mentioned, you can analyze even single molecule, but as you see in this slide, using the tip, for instance, there's some metallic tip such as AFM tip, and you can use the Raman spectroscopy. You can analyze the single molecule, such as this cobalt tetraphenyl 4-free molecule. Okay, but as you see, Raman scattering cross section is very low. It's approximately 10 to the 30s. Okay, because of this reason, you should increase the signal. Also, in a complex matrix, to analyze the target, you should make some purification or isolation procedure. Because of this reason, we are trying to get the signal from the most confident surface. Okay, and this is our latest one of the latest application. How can we increase the Raman signals? I'm going to give some examples. For instance, here, we are using the nanocellulose fiber, okay? We just cast on some glass surface, and then we made some surface like this. You can see some SEM image in here, as you see. Sorry, in here. Okay, and if you also add some nanoparticle, for instance, in here, we add the gold nanoparticle on the nanocellular surface. Actually, gold nanoparticles are embedded in the fibril structure. Okay, then you can modify the surface, actually, what you want. For instance, here, we make some ELISA-like strategy and to analyze or to detect some bacteria species in a complex matrix. Okay, how can we do it? Actually, we firstly coated this gold embedded nanocellular surface. We modified some antibody structure. Okay, I'm going to give this some spatial example also. And then we interacted our bacteria. Okay, then our probe modified gold nanoparticle actually interacted bacteria, and we get the Raman signal of some resulting complex. Actually, you see some Raman map image of the E. coli at a different concentration. Actually, the first one is a very low concentrations, actually A is blank. With the increase of bacteria concentration, as you see, Raman signal intensity is increasing. Actually, we show this as a color change, but I'm going to show the some signal intensity also. But you can map your surface using the Raman image techniques. Okay, if you can easily see that there is a good, very impressive increasing of the signals. Okay, and we can detect the as much as 10 bacteria. Okay, it is very important using this technique and to detect the low bacteria population actually. Okay. And we can construct a calibration curve. Okay, as you see, with the increasing of the bacteria concentration, our search signal intensity increasing regularly, as you see. We also make some selectivity experiment, as you see. This is the expected situation, actually, why we are using the E. coli specific antibody. Okay, and then this antibody only bound to the E. coli in a complex matrix. Okay, and as you see, we observe the highest signal intensity in the presence of E. coli. The other bacteria gives the actually smaller signal as compared to the E. coli signal. Okay, it shows us the very sensitive techniques and very accurate techniques actually. Okay, but also with the collaboration of the Gökhan Demirel from the chemistry department, he actually prepared some nanostructure organic semiconductor film surface. This kind of surface is very hydrophobic, as you see, and this p-conjugated organic semiconductor has got some charge transfer ability. Okay, you can also increase the Raman signals using this kind of substrate. Okay, but there are some difficulties also. Okay, as you see, this is the methylam blue signal as a normal signal, but if you use this substrate, signal is substantially increasing. Okay, and this increase actually, when you compare the other substrates, is very high. As you see, this kind of results. For instance, I want to focus on this bottom graphics. Okay, as you see, with the increasing of concentration, okay, signal is increasing, but we can reach the as low as possible, approximately 10 to the minus 17 molar concentration of the target species. Actually, in here, I remember this is the, I think, rhodomine G. Okay. This means that you can reach the lowest concentration using this kind of substrate. Okay, it means that in a complex matrix, it is possible to use this kind of matrix, maybe, but you can make a simplification system and then you add some substrate, some analyte or matrix to this kind of substrate, and you can weight the signal increase. Okay, and you can detect maybe 10 molecule or 100 molecule. Okay, but in a buffer systems, maybe. How about the complex matrix system? Okay, for instance, blood or saliva. You must do or perform some purification process. Okay, in a buffer system, it looks good, and there is a substantial increase with the signal, okay, using kind of substrate. But in real samples analysis, okay, there is some difficulty actually. In our another application. As I mentioned that SARS is a label-free technique. You can detect without using a label. You can detect a target, okay? For instance, you can detect a virus, or you can detect the bacteria or toxin, but you can use a special probe, such as aptamer, such as antibody, or another probe, okay? Because the selectivity is the most important parameter here. Actually, here we demonstrated that you can use the, for instance, boronic acid substrate just bound to the bacteria samples. Okay, then remove the bacteria from the matrix and then apply the simple laser. Okay, and you can get the signal. As you see, we can get some bacteria species signal. Okay, bacteria regarding signal. But it is not possible to analyze the bacteria in a complex system using the label-free SARS strategy, because this signal is a array signal, and all the other species may contribute to this signal. Okay, because of this reason, we prefer the labeled system actually. I am also going to show some label-free applications such as glucose. Okay, for instance, we are using here some paper substrate, and this substrate, some nanoparticle is embedded on it. Okay, so, I remember these are the gold nanoparticles, and you can observe some Raman signal with the increasing concentration of the glucose. Okay, and you measure you are able to measure the glucose concentration in blood. Okay, this is also label-free technique. But you can separate the other component at the beginning of this paper. Okay, in here, for instance, some blood is trapped at the beginning of the here. Okay, in a channel, like this is the paper, but there is a channel here. Okay, using the wax printer, we make it some channel. As you see, some blood is entrapped, or some cell, especially big cell, is trapped here, and small molecule is able to move to end of the line. Okay, and you can detect some target spaces from the here at the bottom side. But you can optimize all the area. Okay. Okay, these are all our latest applications, the label-free application. For instance, this is the some of the actually protein analysis. Okay, I'm skip this one. This one is also a label-free application of some TNT sample or ischemic sample. Is a very dangerous chemical, as you know. Okay, so some explosive detection using this similar strategy with the increase of the analyte. Okay, for instance, TNT. You can observe the increase of the signal. Okay, for instance, in here we are using this. We are trying to construct a calibration with the increase of RDX concentration, and here we are using the HMX concentration, but the matrix is very complicated here, complex actually. What was our matrix? Is a soil matrix. Okay, it's difficult to analyze actually in a target spaces such a matrix. Okay, and this is our SARS labeled analysis strategy. Actually, this is like an ELISA strategy. Okay, what we are doing is here, just we make some substrate here. Okay, for instance, silicon substrate. We modified this substrate with using some polymeric structure actually. In here, with the collaboration of Professor Tuncay Çaykara from the chemistry department, okay, and we construct some modification of hybrid silicon substrate with using the raft polymerization, and then we make some probe molecule on the substrate. Okay, we modified the probe molecule. Okay, for instance, here we are trying to analyze the hepatitis B virus. Okay, DNA. First of all, you modified your substrate with a suitable probe. Okay, after making sandwich hybridization, you can get the signal from your Raman system. Okay, and here you can see the calibration curve actually. As you see, we can detect up to femtomole level of hepatitis B virus DNA. This is very important actually when you consider the low detection limit. Okay, you can also see that there's a very high selectivity of our systems. Okay, this is the label technique. This is another label techniques. This is the same strategy, only we changed some substrate. Okay, some actually probe. In the previous one, we used the selectively the aptamer probe, but here we just used some cyclodextrin unit. Okay, to catch the target from the matrix. This is another example actually, but the strategy is the same. Okay, as you see, this is our calibration curve, and we can actually reach the nanomolar concentration of some pyram molecule. Okay, this is our selectivity. As you see, selectivity is not good here because beta cyclodextrin unit is not selective when you compare the aptamer or anticore. Okay, but this is the proof of concept demonstration, as you know. You can also detect some virus system in a complex matrix. Actually, you can also detect using this strategy to COVID-19 virus. Okay, this is some strategy. But I want to mention that serological tests such as ELISA tests, because we are using the anticore, antibody, and antigen interaction. Okay, there are a lot of cross interaction. Okay, and they give us some non-specific interaction and give an extra signal. And our system accuracy is not good actually. Because of this reason, we are making some purification process. Okay, in here, for instance, we made some paper purification system to eliminate the other matrix, other component from the system. And then we are using some selective antibody. Okay, and this selective antibody catch the target from the matrix, and then using for instance, you can use some magnetic nanoparticle, and then you remove the analyte from the system, and then you can make some measurement using the label. Okay, this is the only one example of our latest application. Actually, we in here we use the potato virus. Okay, this is another application actually. We also make some another chip application. We are capable of constructing a chip surface. Okay, and for instance, you see there's we constructed a passive chip. Okay, in here there's a 4-chamber. This is like an ELISA, okay, but this is a miniaturization ELISA. And in here, for instance, in first chamber, we interacted the target, and the second chamber we make some washing procedure. Okay, and in third chamber also we make some interaction with the label, and the last chamber is a measurement chamber, is like that. Okay, as you see, this is the we constructed this kind of capillary with the collaboration of Ander Yildirim from Matthew. Okay, then we can analyze, for instance, a hormone or protein or bacteria using the same strategy. But the main important thing, there should be a purification step before the entrance of the chip. Okay, because most of the people look at the literature and say that chip is easy and there are a lot of advantage, but there's also some disadvantage. I think the most difficulty is the handling of the chip system. Okay, we also make some calibration curve. I'm going to skip this one, okay, because our time is very limited. And I'm going to give some merit of analytical system. As you see, we compared our system with the other system. Our method also reached the low deduction limit, actually. Okay. And we also make some label-free analysis of using the same system, but it works. But sometimes there's some problem. For instance, this chip system is very small. Okay, you can fix it under the microscope, and you just focus on the measurement area of the system. Okay, then you can get the signal. As you see, when we interact with the bacteria, with the antibody modified nanoparticle, you can get the signal. As you see, with the increase of the signal, with the increase of the target, sorry, and you can easily see that our Raman signal intensity with increasing, okay? And we can reach the approximately 10 bacteria detection limit level, okay? This is very important, actually. Okay, and we have a lot of application, but now I'm going to skip other application. Okay, because tomorrow my student Hassan will talk the details of the paper-based electrode, and I would like to thanks to my partners, especially my project partner. I would like to thank the Ismail Hakkı Boyacı and other partners, and I'm going to thank my students and postdocs. Okay, thanks for your attention. If you have any questions, please. Okay, I'm just. Okay. And our next speakers, Professor Dr. Irfan Ar. Can you hear me, Professor Irfan Ar?
Sayın Hocam.
Evet.
Hocam siz host olduğun için gelenleri kabul etmeniz lazım. Bayağı bir şey geldi, geri çıktılar.
Ya ben şimdi göremedim onları.
Hocam İrfanlar Hoca geldi, diğerleri geldi ama siz almadığınız için geri çıktılar. Hocam bundan sonra sağ tarafa o participant'a tıklayıp yan tarafta açılan sütundan gelen hocalarımızı kabul ederseniz biz de bilgilendiriyoruz şu anda Sayın Hocam.
Tamam da ben şu ekranı bir türlü büyütemiyorum ya, kusura bakmayın. Ne oldu ben? Bir dakika.
Hocam hostluğu bize tekrar teslim edebilir misiniz? Görebiliyor musunuz bizi yan taraftan?
Make host mu diyor?
Evet, make host yapın hocam bizi.
Change host yaptım, evet.
Tamam Sayın Hocam, biz alıyoruz hepsini hocam.
Tamam, teşekkür ederim.
Uğur Hocam devam edebilirsiniz siz şeye. Oh, İrfan Hocam burada zaten.
Okay. Welcome to our session again. Sorry, there's some problem in my computer. Okay, our next speaker, Professor Dr. Irfan Ar from the Gazi University Chemical Engineering Department. Okay, you can share your slide, Professor Irfan Ar. Can you hear me, Professor?
Yes. But I try to share my presentation.
Okay.
Yeah.
Okay. Thanks for your attention, by the way.
Clearly?
Okay, you can start.
Thank you, dear Chair. Good morning, everybody, from a shiny and warm Ankara morning. I would like to thank especially to the whole people that spent effort organizing to this conference, to all esteemed and well-experienced attendees that participating their studies with us, and especially to the invisible heroes, the technical staff behind all these studies. Details of our studies will be given by other members of our team, the Associated Professor Dr. Alpay Şahin, and my PhD students Aygün Çalı and Yavuz Atlı in their speech. Therefore, I try to give you a general perspective about the hydrogen and the fuel cell technologies, and also try to draw a perspective, a general perspective about the futures of the hydrogen and fuel cell technologies. In fact, it may be better to say that about the hydrogen economy, because hydrogen economy provides them huge number of job opportunities, both by white collars and the blue collar peoples. And let me continue. Yeah, it nearly becomes customary to start the speech or the articles about the renewable energy to indicating that fossil fuels are very harmful to human health and environment, and also they will be exhausted in the 21st century. Therefore, a new and renewable energy source must be found. Do you agree with these two ideas? But I want to look at this picture in different perspective. What are the fossil fuels? They are the petroleum, coal, and natural gas. Unfortunately, these fossil fuels meet the 80% of the world energy demand. But at the same time, they are a very valuable chemical source. These chemicals are aspirin, chewing gum, chicken nuggets, clothing, dentures, lipsticks, wax, shampoo, solar panel, toothpaste. This list can be extended to 100 of products from your daily life. And if you look at your environment, you can see that the various materials that are made of the petroleum derivative substances. Therefore, petroleum is called as the blood of earth. Therefore, use of fossil fuels as fuels means waste of air. No. I am not defender of the fossil fuel, but I try to give Caesar's right to Caesar. Okay? On the other hand, what about the dark side of the fossil fuels? Percent of the world's energy is supplied by fossil fuel. If countries continue to grow, need for renewable energy sources does too. The International Energy Agency states that the need for fuel will double within the 50 years. Sustainable fuel to the chemical disaster. You can see this picture very clearly. You can see that the number of vehicles in worldwide is.
Thank you so much, Turan, for your nice presentation.
Oh, sorry, but
dear audience, any question?
From them. Would you have to close their switch of their microphones? Because it's confused. Thanks. Okay, if you look at this picture, there are 1,429,018,346 vehicles, and this number increases 1.5% every second. This means that those much of the vehicles emitted 103.06 tons of carbon dioxide per second. This is a huge number and very dangerous. Increase of carbon dioxide emission means growing need for the mobility, and it leads to climate change. You see, result is this. And in capital of South Korea, Seoul, people cannot live without mask. Therefore, South Korea decided to close their thermonuclear and the thermal power centrals. Instead, they tried to build up a new 2 fuel cell power station. Okay. Air pollution kills 400,000 people in Europe every year. Pollution, climate change remain Europe's top environmental threats to health, say European Environment Agency. You can see here, 1 liter of diesel, when you burn it in your internal combustion engine of your car, you emitted 2.62 kilograms of carbon dioxide. For gasoline, it may be smaller than that, but also it is very, very dangerous. And opposite of the Kyoto protocols or the Paris agreements, global governments plan to produce 120% more fossil fuels by 2030. drastically and also within the 2.7 degrees or the 1.5 degrees Celsius warming limit, the OH under the 2015 Paris Agreement. All major fossil fuel producing nations, including the United States, China, Russia, Saudi Arabia, India, Canada, and Australia, have ambitious plans to increase production, according to a new report by a leading research organization and the United Nations. Carbon emissions from fossil fuel use totaled 37.1 billion tons in 2018, in a new record. Substantially reducing those emissions will never happen without reducing fossil fuel production, says Mitchell Lesser, the lead author of the Production Gap Report and the director of Stockholm Environment Institute of Center. Yeah, in order to prevent all these disaster scenarios, we have to find out a new energy source that support the sustainable industry and sustainable development of the society. This new energy source should have these properties: non-toxic, renewable, environmentally friendly, safe, economic, and provides the security of supply. All these properties made by the only one fuel, that is hydrogen. Yes, the ancient element. Before the life started in the earth, hydrogen exists in the universe. But unfortunately, it cannot be found alone. On Earth, hydrogen is found more complex molecules, such as water or the hydrocarbons. Therefore, it must be extracted from these molecules. Hydrogen, in fact, is not a source of energy, but an energy carrier. And it allows the transport of energy in a usable form from one place to another. Hydrogen, like electricity, is an energy carrier that must be produced from another substance. Therefore, hydrogen and electricity is called as the secondary sources or secondary energy. Before the fuel cells developed, we already produce hydrogen in order to produce these materials. For example, in world, in 2019, around the 60 million cubic meters of hydrogen is produced, but its 25% is used to production of ammonia. The other 25% is used in the refineries, petroleum refineries, and production of methanol and the other chemicals. You see, if you pass to the hydrogen economy, this means that you need this amount of hydrogen beside the hydrogen needed as a fuel for those number of vehicles. Therefore, there will be a new renewable, environmentally friendly technologies in order to produce the hydrogen. In order to understand how many tons of hydrogen is needed if all vehicles in the world are transferred to the fuel vehicles. Global hydrogen production for chemical uses, 45 million tons. Please note that these values are given taken from the 2005, and it increases nowadays to around 16 million tons hydrogen production per year. And 1 ton of hydrogen carries 142 gigajoules of energy. But we know that approximately 1 fuel cell can travel, if you make the fuel economy, 60 miles by using 1 kilogram of hydrogen. And ordinary people drive an average of 15 miles a year. Therefore, annual hydrogen demand is 250 kilograms per year. This is for one vehicle. And if you divide this hydrogen production to the one vehicle demand, you can obtain that this amount of hydrogen can only support 180 million cars. This is about the 25% of the number of cars in the worldwide. On the other hand, we have the other demands for the hydrogen. And in the upper hemisphere, you can see the hydrogen production methods. On the below hemisphere, the demands for the hydrogen is appear. You see, we have the large number of renewable hydrogen production technologies, biomass, solar thermal or solar photovoltaic, hydrogen dynamic, and also the wind. You may count within the renewable technologies or not, but also nuclear power central are used also the production of hydrogen by using the thermolysis technologies. Nuclear heat also use the thermolysis technology in order to produce the hydrogen from the water. But unfortunately, 84% of the hydrogen is produced by using the fossil fuels. This means that in next 2 or 3 decades, we still need to use fossil fuels. Therefore, we have to develop the clean energy technologies in order to produce hydrogen. Numerous processes for the production of hydrogen include the chemical, electrolytic, thermolytic, photolytic, biological. Besides this, under the large number of technologies for the hydrogen production are tried to develop in the laboratories. Cycles such as sulfur iodine or copper chlorine or sodium chlorine, iron chlorine, magnesium iodine, vanadium chloride, and copper sulfide, and the hybrid chlorine are commercially recognized after considering numerous factors like availability and abundance of the materials, their viability, thermodynamic feasibility, and the safety issues. Here, some of these technologies appear here. The figures show their approximate quantities. Natural gas reforming, most widely used technology, around 50% of the hydrogen production is realized by using natural gas reforming or steam methane reforming technologies. On the other hand, biomass gasification and the electrolysis, the electricity supported by the wind energy, or coal gasifications with carbon capture technologies, electrolysis, high temperature electrolysis or thermolysis, and solar energies. Large number of solar technologies are used in the production of hydrogen. For example, solar energy used for the dissociation of the water by using thermolyzing technologies, or solar thermocouple cycles may be used. Solar together with the fossil fuels, solar energy together with the fossil fuels may be used for the dissociation of the water into the hydrogen and oxygen, and solar reforming, solar cracking, solar gasification, etc., etc., etc. Besides this, after the, of course, development of the biotechnology, we have the bio-derived liquids microbial biomass conversion. these technologies are all together try to meet the future hydrogen demand of the humankind. Here you can see nearly all of the commercial and the developing technologies for the hydrogen production. There are several studies in the laboratories in order to produce hydrogen in a renewable manner by using renewable environmentally friendly technologies. For example, the proton exchange membrane electrolysis and alkaline electrolysis or solid oxide electrolysis technologies. And finally, microbial electrolysis technologies are used for the hydrogen production. But there are some new technologies also in laboratory stage that combines the catalytic processes together with the bioconversion technologies. But they still have a very, very low efficiency. Therefore, there is not any commercial process by using these technologies. The very widely used technologies appear in this table. You can see that the steam reforming, very well known and well established technology, who has the very high efficiency around the 70 to 85% efficiency, partial oxidation, autothermal reforming, and the plasma reforming, etc., etc., etc. But please note that in these technologies, the hydrogen purification or the carbon capture technologies are not involved. The hydrogen economy is nevertheless slowly developing as a small part of the low carbon economy. As of 2019, however, hydrogen is mainly used as an industrial feedstock, primarily for the production of ammonia, methanol, and petroleum refining. Hydrogen gas does not occur naturally in convenient reservoirs. This is maybe one of the main difference between the fossil fuels and the hydrogen. Fossil fuels, as you know, that fossil fuel reservoirs are located in certain locations of the earth. And the countries having these reservoirs use these resources as a political press factor. We see it's one example. In 2016, Russia used natural gas reserves as a political factor against the euro. And also Iranians sometimes use it against us. Anyhow, hydrogen can be produced various sources, and all countries have resources to produce the hydrogen from the renewable technologies. For example, wind, solar, wave, or the hydro, and other kinds of primary energies in order to produce hydrogen. Therefore, hydrogen is known as the freedom energy or independent energy. Okay. Steam reforming of natural gas includes about half of the hydrogen production, and hydrogen price is about $7 US per gigajoule. A comparable price for hydrogen is provided by partial oxidation of hydrocarbons. However, greenhouse gases generated by thermochemical processes must be captured and stored, and thus an increase in the hydrogen price by 25 to 30% must be considered. The price of hydrogen from gasification of biomass range from the 10 to the 14 US dollars per gigajoule, and that from pyrolysis, 8.9 to 15.5 US dollars per gigajoule. It depends on the equipment availability and the cost of feedstock. Electrolysis of water is one of the simplest technologies for producing hydrogen without byproducts. Electrolytic processes can be classified as highly effective. On the other hand, the input electricity cost is relatively high and plays a key role in the price of hydrogen. Therefore, these processes should be developed. At least their efficiency must be increased. For instance, filling a hydrogen fuel cell vehicle in California costs around $16.50 per kilogram compared to the $3.232 per gallon of regular petrol in the same state. Light-duty fuel cell electrical vehicles are typically 2.5 times more fuel efficient than the comparable gasoline-powered vehicles, which means that achieving price parity with gasoline would require that 1 kilogram of hydrogen sells for not more than $8.08. In other words, hydrogen costs need to fall by 50% by becoming competitive with the fossil fuels. Therefore, it is necessary to immediately increase the efficiency of these environmentally friendly technologies, especially production of hydrogen by using the renewable energy sources. 1 kilogram of hydrogen with specific energy of 143 megajoule per kilogram, or about 40 kilograms hour per kilogram, requires 50 to 55 kilowatt hour of electricity. Therefore, new methods are under the investigation. There are various new developed technologies here, but please remember that these are still at the laboratory stage. There is not any commercial stage that is established by using these production methods. Fermentative hydrogen production is the fermentative conversion of, please note that since we have the steam reforming technology that is a well-established technology, the biogas produced from the anaerobic digesters of the biomass can be converted to the hydrogen by using the steam reforming of the methane after the biogas is purified. Due to this high-cost purification process, still this hydrogen produced in this manner cannot be competitive to the fossil fuels. Yes. Biohydrogen manifested by a diverse group of bacteria using the multi-enzyme systems involving 3 steps similar to anaerobic conversion. Dark fermentation reactions do not require light energy, so they are capable of constantly producing hydrogen from organic compounds throughout the day and the night. Photofermentation differs from dark fermentation because it only proceeds in the presence of light. For example, photofermentation with Rhodobacter sphaeroides can be employed to convert small molecular fatty acids into hydrogen. Electrohydrogenesis is used in microbial fuel cells where hydrogen is produced from organic matter or solid matter, while 0.2 to the 0.8 volt is applied. You'll see a very small energy requirement exists for the hydrogen production by using microbial fuel cells or the microbial electrolysis devices. There are some other procedures. For example, the microbial fuel cell and variety of aquatic plants used in these electrolysis systems. For example, bread, sweetgrass, corngrass, rice, tomatoes, and lupines, and the microalgae especially. Because the recent studies show that microalgae can also used in the microbial fuel cells in order to capture the heavy metals. So it may be ideal for the treatment of the wastewater, especially exhausted from the industries. Both wastewater treatment, elimination of the heavy metals, and production of electricity or the production of hydrogen, of course, can be carried out by using the microbial fuel cells. And high pressure electrolysis is the electrolysis of water by decomposition of water into oxygen and the hydrogen gas by means of an electric current being passed through the water. The difference with a standard electrolyzer is the compressed hydrogen output around 120 to the 200 bars through the process known as chemical compression. That the need for an external hydrogen compressor is eliminated. The average energy consumption for internal compression is around 3%. Therefore, it provides the energy saving in great extent. There are some other things, but I saw that I have not enough time to pass over all these technologies one by one. But before that, another important item, that is the hydrogen storage and fuel cells, should be worthwhile to take here. Hydrogen has the lowest energy per unit volume compared with the other hydrocarbons. For example, 5 buckets of water contains 5.5 kilograms of hydrogen. This amount of hydrogen can take a fuel car approximately 600 kilometers. Only exhaust gas is the water vapor. If you use fuel cell, of course, in your car, because we know that if pure hydrogen is your fuel, the output of the fuel cell is electricity, and the side products are the heat and water vapor only. Up to here, everything is okay. There is no problem, it seems so, but in fact, density of hydrogen at ambient conditions is 0.09 grams per liter, or the kilograms per cubic meter. Fuel cell passenger cars currently have a range of around 500 kilometers or more than 300 miles. With the current vehicle technology, this requires around 4 to 6 kilograms of hydrogen, depending on the vehicle, driving style, and the driving conditions. A passenger car, therefore, needs a tank capacity of around 100 to 150 liters to store 4 to 6 kilograms of hydrogen at 700 bar. The petrol tanks are modern, compact, and mid-size of cars have a capacity of 50 to 60 liters, while executive cars and light commercial vehicles carry 70 to 80 liters of fuel. This means that we have a hydrogen storage problem. Hydrogen storage problem is serious, especially for the mobile applications. This may be more clearly seen here. The density at ambient. Hydrogen has 0.09, methane 0.72, and the hexane has 703. If you look at the ratio of the densities, 1/10,000. In fact, the light density is this much of low density is advantage in some aspects, especially in the safety aspect. But on the other hand, for the storage, it becomes a serious problem. Hydrogen storage technologies can be divided into physical storage, where hydrogen molecules are stored, including pure hydrogen storage via compression and liquefaction, and chemical storage, where hydrides or the hydrogen stored as the chemical substance. Here, a summary of these storage technologies appear in the figure. Physical base are the compressed gas, cold or cryo, compressed and liquid hydrogen. On the other hand, we have the material-based chemical storage by using the adsorbent, for example, the metal organic frame substances, liquid organic materials, for example, methyl cyclopentane, and interstitial hydrides, lanthan nickel hydride, magnesium borhydride, sodium borhydride, etc. These are the complex hydride. In fact, sometimes we may have the 3 or more hydrides, species in a complex hydrides, and chemical hydrogen, hydrazine, ammonia, etc., can be counted in the chemical hydrogen storage. Here, some special apparatus are seen for the gases and the liquid hydrogen storage. And Japan have a liquid hydrogen storage facility at the terminal in Kobe. Are expected to receive the first shipment of liquid hydrogen via liquid hydrogen carrier in 2020. Hydrogen is liquefied by reducing its temperature to minus 253 degrees Celsius, similar to liquefied natural gas, which is stored at minus 162 degrees Celsius. A potential efficiency loss of 12.79% can be achieved, or 4.26 kilowatt hour per kilogram out of 33.3 kilowatt hour per kilograms of hydrogen. You see, we spent much of the large amount of the energy that is contained within the hydrogen spent only for the either compression or the liquefaction of the hydrogen. And I do not want to talk details about this one because they are the very well known and the widely used technologies, but there may be some new technologies. For example, the xenon, noble gas. It is unreactive to the other materials, but Carnegie Institution have found the first time that high pressure can be used to make a unique hydrogen storage material and similar things. Of course, carbon nanotubes, single nanotubes or the multiple nanotubes on the graphene and the fluorines, etc., are the new types of storage materials. But please note that still they need to further development because the per unit mass of these materials contains only a small amount of hydrogen. But you know that the weight is very important parameter in cars. If weight increases, the energy required to move these materials becomes much larger. Therefore, the amount of hydrogen that can be stored per unit kilograms of material must be high as much as possible. Metal organic frameworks, another, and you can see the ligands of the metal organic frameworks for the hydrogen storage. Clatrate hydrides, glass capillary airways, glass microspheres. These microspheres are tried to use in the Army, in United States Army for the mobile applications. Metal hydrides, this may be a very promising technology because the light metals, lithium, magnesium, etc., are used for the hydrides. And also, it may be a chance for Turkey because you know that we have the very huge boron reservoirs. Therefore, the boron hydrides are the promising technologies for the storage of the hydrogen. You can see here some other new technologies for the storage of the hydrogen. And is hydrogen safe? After the Hindenburg disaster in 1937, people are afraid of to use hydrogen because it is very explosive. But is it really so dangerous and very explosive? We know that hydrogen gas is colorless, odorless, and not detectable in any concentration by human senses. This means that you cannot aware about the hydrogen burning unless you touch it. Hydrogen is non-toxic, classified as simple asphyxiant, and has no threshold limit value. Hydrogen is not listed as a carcinogen by the National Toxicology Program, International Agency Research on Cancer, or Occupational Safety and Health Administration. For historical reasons, hydrogen has a bad reputation, which is not justified as a more recent analysis of the Hindenburg airship catastrophe proves. Airship caught fire because of a highly flammable skin material in those pre-polymer times, and not because of the hydrogen filling gas. Disaster is not due to the hydrogen used as the filling gas, but due to the flammable skin material. This safety of hydrogen relies on its high volatility and non-toxicity. Please note that ignition range of the hydrogen is very, very wide, so it seems to be very dangerous. You see, in the mixture of air, only 4% to the up to 75% of hydrogen flame. But in fact, in open air, you cannot reach these concentrations, even 4%. What does safe mean? Do you think natural gas is safe? Please look at here. Pipeline transport and distribution. Between 1986 and 2003 years, 2,406 accidents related with gas distribution, 300 deaths, 1,364 injured, and $302,504,095 financial damage, and 1,467 accidents involving gas transportation, 60 deaths, 230 injured people, and 365,433,478 financial damage. Do you think gasoline pipeline transport is safe? Please look at these figures. Between only 1986 to the 23, 3,302 accidents, 37 deaths, 254 injured, and 857,432,100 financial damage. This amount of dollars are lost. Precious gasoline pipeline, you see, it is an environmental disaster. The very dangerous hydrocarbon emission together with some particulate emissions. Which one is safe? Here you can see the burning of a gas station in Nevada. 5 gas stations are thought to be caused mostly by mobile phones, cell phones. And you can see here injured and the dead people, numbers of injured and the dead people, and also the property lost during these disasters. And Mexican Gulf, shell companies' oil well, causes this disaster. At this dock, oil with this petroleum leakage. Here, propane delivery track is under the fire. These examples may be extended to the large numbers, and the injured or the dead people's number may be given from the other safety or the fire protection agencies. But what about the hydrogen? There is no common consumer complaint that or damage record known to date. No, hydrogen is widely produced in the world. 9 million tons of production per year, about 600 miles of pipeline exists in the United States. Routine transportation with trucks and, of course, some accidents, but not many, occur during the transportation of the hydrogen and also production of it. No reported cases. Often, most of the accidents related to other fuels. Hydrogen has very safety features. It is difficult for it to form an explosive mixture with air because it has a very low density. Its diffusion rate is very, very high, and its escape to the space whenever it's leaked from any pipeline or any container. A limited volume is required for usage because it has a very huge energy content per unit mass of it. This is a good example. In this experiment, a fuel cell car and a gasoline-fueled car are ignited at the same time. After the 3 seconds, you can see that whole of the below section of the fueled car, gasoline-fueled car, is covered by the flame. On the other hand, you see hydrogen-fueled car is not affected this flame. And after the 60 seconds, you see most of the gasoline-fueled car is damaged. And the people within this car cannot escape safely in these short times. And after the 90 seconds, the gasoline-fueled car is completely fired. But there is no any damage in the hydrogen-fueled car, but due to the cease of the hydrogen emission, the height of the flame has become shorter. Somewhat different conclusions are presented in Barber, who argued, for example, that a hydrogen leak would be less dangerous than a natural gas leak, suggesting somewhat unexpectedly that a hydrogen explosion would be less severe than in the case of other fuels, as hydrogen has the lowest explosive energy per unit of the fuel. And we have some other details, but I want to talk a little bit about the fuel cells. There are 2 types of technologies for the end use of the hydrogen, other than, of course, production of the other chemicals: direct combustion and the fuel cell. Hydrogen can be combusted in appropriate appliances or modified internal combustion engines, and also it can be used as fuel in the fuel cell. Fuel cells are the technologies that convert the chemical energy of the hydrogen and oxygen directly into the electricity throughout the 2 electrochemical reactions. Fuel cells are the devices that convert fuel directly into the direct covered electricity. Directly is important because it provides the high energy conversion for the fuel cells. In internal combustion engines, we have the maximum efficiency of around the 30%. But in fuel cells, theoretically, we can reach up to the 83% of efficiency. But when this energy is converted to the moving parts of the automobile, in that case, this efficiency drops up to the 42 to the 36%. To process an electrochemical reaction similar to battery, unlike battery fuel cell does not store the energy with chemicals internally. Instead, they use a continuous supply of fuel from the other sources. There are different types of fuel cells. Fuel cells can be classified according to the operating conditions, for example, high temperature fuel cell or the low temperature fuel cells, or depending on their fuels. But most widely, they are classified according to the electrolytes used within. For example, polymer electrolyte membrane fuel cell. Membrane is behaved as the electrolyte. Direct methanol fuel cell, it may be regarded as a subclass of the proton exchange PEM fuel cell. But some scientists say that it may be included in the direct alcohol fuel cells because there are some direct ethanol fuel cell, direct propanol fuel cell, etc., etc., etc. Solid oxide fuel cell, molten carbonate fuel cell, alkaline fuel cell, and the phosphoric acid fuel cells. As a short, we can say that you have different types of fuel cells in order to use everywhere where the electricity is used. You can provide the power for your phone cell or the laptop to provide the need of electricity of a city. Okay? For example, solid oxide fuel cell can be replaced by the thermal power plants. The most widely used fuel cell is the PEM fuel cell. Here you can see that its parts appear here. Like the other batteries, it has two electrodes, anode and cathodes, and have the electrolytes as the membrane. Of course, we need the catalyst because PEM fuel cell operates around 80 degrees Celsius at these very low temperatures. In order to extract the electrons of the hydrogen, we need the highly effective catalyst, for example, platinum, palladium, or the radium, etc. And here you can see the operation of a fuel cell. Hydrogen fed to the anode, divided into the protons and electrons. Electrons are connected to the cathode by an external circuit and producing electricity, whereas the protons are passed through the proton exchange membrane to the cathode. At cathode, the electrons come from the external circuit, and the protons from to the membrane and the oxygen fed to the cathode are combined to give the water. You see, this is a reversible process because you can send this water to the electrolyzer to get again hydrogen and oxygen. This only side product is heat. Therefore, you may see that a bird drinking water and exhaust of a car, of course, if it operates using fuel cell. But in a single fuel cell, the energy obtained is very, very small. Therefore, a large number of fuel cells should be combined to form the stack. Nowadays, most of the scientists try to find out the problem related with the temperature and the water management, heat and water management problems. Because to provide the uniformity of temperature throughout the whole stack is very important. And on the other hand, the humidity of the cell is very important since the transportation of the protons provided by the water molecules throughout the membranes. Anyhow, I want to talk a little bit about the future of the fuel cells. Some researchers point to establishment of the Hydrogen Council at the World Economic Forum in Davos as the key development in 2017 in the industry. Hydrogen Energy Council has set the following target fuel cell vehicles for the 2035. 350 trucks, 15,000 buses, thousands of trains and ships, 1 over the 12 castles in California, Germany, Japan, and South Korea. This means that 100,000 of car operates with the fuel cell. And these targets are envisaged for fuel cell vehicles for 2015. 15 to 20 million commercial truck, 5 million bus, 25% of passenger ships, 20% of whole trains in worldwide, and the 400 million cars. Oh, sorry, we not have enough time. Dear Chair,
we have time, Professor Irfan, because the next speaker is absent now. Okay, you can continue, please.
Thank you so much. On the other hand, Department of Energy predicts that hydrogen conversion will not be fully accomplished until 2015, but that employment in the fuel cell and hydrogen sector will increase by 0.37%. That is 675,000 jobs will be created. For example, by 2035, 10,000 white-collar jobs will be created in the production of auto parts, while this figure will be 12,000 by 2015. And for blue-collar employees. Blue-collar workers working in automotive part production, including displacement in the oil sector, of course, are expected to be 104,000 by 2035 and 170,000 by 2050. This maybe. This means that it must be. The biggest job activities occur to be expected in the automobile sales and repair segment, with the 436,000 by 2015 and 620,000 by 2050. Fuel cell passenger cars currently have a range of around 500 kilometers or more than 300 miles. Within the current vehicle technology, this requires the 4 to 6 kilograms of hydrogen, as I said before. But we have a viscous cycle, chicken or egg hatch, or you may say that egg or chicken viscous cycle. Because there's no hydrogen infrastructure is not sufficient. So I want to buy a fuel cell car, but it is not practical. There is no sufficient number of fuel cell cars in traffic. Therefore, to make investment for the hydrogen infrastructure is not feasible on the other end. You see, in order to overcome this vicious cycle, some famous Japanese firms, Nissan, Honda, Toyota, are combined their powers and take a very big funds from the Japanese government in order to establish a hydrogen infrastructure for whole Japan islands, because otherwise they cannot sell their cars. Happily, 2019 saw refueling infrastructure grow in all the main early adopter regions, including Japan, Korea, California, China, Germany, and other parts of Europe. But the pace of vehicle versus station rollout is quite different in each one. In Germany, one hydrogen refueling station serves fewer than 10 cars on average. In the United States and the Korea, the ratio is about 130 cars per hydrogen refueling stations. Some stations in California are visited so frequently that they can run out of hydrogen and need to be upgraded. This shows the importance of the hydrogen storage. Japanese stations service about 30 cars per hour. Dear Chair, somebody want to connect to our session from Italy. Would you please accept?
Yes, we are trying to get the host. Yeah, we are trying, Professor. You can continue.
Thanks. The equipment suppliers have worked on improved offerings to allow quicker rollout and add flexibility. Air Liquide will launch a skid-mounted hydrogen refueling station in the United States. In California, we know that a very big highway is equipped with the hydrogen refueling station, and this highway is called the High Road, Hydrogen Transportation Road. Compact and intended to be mobile, it should suit temporary installations, small fleet usage, vehicle testing, or location testing. Fueling capacity is up to the 200 kilograms hydrogen per day and up to the 5 fuels per hour with the capability of 2 to the 7 kilograms per fuel. Average tank capacity is known as the 5 kilograms. Quebec City has taken delivery of Powertech's new hydrogen station in a box. 28 feet containers, 700 bars hydrogen refueling station designed for rapid deployment with minimal site preparation. It can deliver 4 consecutive fills of a typical passenger car, should fill around 20 vehicles per day. All these things are necessary. Why? For example, Denmark decided to change whole tax affiliates with the fuel cell car. And the first tax affiliate is converted from internal engine car to the fuel cell car. You'll see the filling station net is increased day by day. Therefore, hydrogen storage and the hydrogen production beside the hydrogen refueling station gains big importance. On the heavy-duty side, McPhy launched its new augmented McFeeling flexible hydrogen refueling stations architecture in modular units of 2,000, 4,000, and 10,000 kilogram hydrogen per day. They provide so much hydrogen per day. According to the hydrogen mobility program of the Germany, 78 hydrogen filling stations were operating in Germany by December. 9 more are in trials, 3 in the execution phase, and 5 of them in approval stage, and 10 station is in planning stage. Germany should reach its hydrogen stations goal by mid-2020. Frustratingly, only just over 600 fuel cell electrical vehicles are on the roads. Across other European countries, approximately 50 hydrogen refueling stations have been added in 2019. By 2025, the National Energy and Climate Plan's target to the 750 hydrogen refueling stations by 2025. This includes Germany's target of 400 refueling stations by 2025, given sufficient rollout of vehicles. We know that from newspapers and the energy magazines. United Kingdom break the records about the decarbonizing days. And their plans to do also to pass to the renewable energies, especially for the hydrogen filling stations. And California added relatively few stations between end of the 2018 and early December. Open stations grew from 39 to the 44. This is a slowdown of rollout compared to the development projects by the 2018, which was for the 64 stations in 2020. You see, a good example for the hydrogen refueling stations, because the energy requirement is provided by the solar photovoltaic cells. And this is another refueling stations for the fuel cell track. On the other hand, for other purposes, not only for the transportation, but for the usage of, for example, the uninterrupted energy demand. You see, huge number of fuel cells are sold throughout the whole worldwide. Here you can see the amount of fuel cells shipped throughout the 2014 to the 2018. Please read all these numbers by multiplying the 1,000.
Okay, Professor Irfan. Professor Irfan, we have 1 minute if you wish.
Okay, as a result, we can say that in order to prevent the environmental disaster and to prevent the climate change, we have to change our technologies from fossil fuels to the renewable energy sources. These sources should be both renewable and also supply the sustainable development. And the most promising alternative energy seems to be hydrogen, but it has some challenges to overcome. For example, we have some problems in the storage, some problems in the transportation, and also some problems related with the end use of the hydrogen. Therefore, we have to develop these technologies in order to come into the picture, the hydrogen economy. I want to again thank to all attendees and all esteemed audience. Thank you. Special thanks for you and the other organizing committee and members. Have a nice day.
Thanks for your attendance. Actually, any questions, audience?
Just thank you.
Okay. Actually, Dr. Irfan, I want to ask one question regarding the capture and emitter of the some system. You mentioned that steam reforming is the best one for the hydrogen storage. Okay, but if you use the bore, for instance, capture is important, but emission also important step. What do you think?
I said that the most widely used technology is nowadays, according to the data technologies, is the steam reforming technology. And the steam reforming technology is used to production of hydrogen from the natural gas and the methane.
Okay.
If you use the natural gas as the resources for the hydrogen production, in that case, you need to make some purifications. For example, at the initial stage, you have to remove the sulfur content of the natural gas in order to prevent the corrosion of the whole equipments within your hydrogen production system. For example, high temperature or low temperature water shift reactors and catalysts within them. In order to prevent their corrosion, you have to remove the sulfur within the natural gas. And also, there are some carbon dioxide emissions. In order to carbon monoxide emission also, we know that in PEM fuel cell especially, we use very costly, very expensive catalyst, for example, platinum.
Yes.
But platinum resistance to the carbon monoxide is very, very low. At the operating conditions of the PEM fuel cells. Platinum selectively absorbs the carbon monoxide rather than hydrogen. This means that our catalyst is poisoning.
Yes.
It loses its activity and fuel cell efficiency drops significantly. Therefore, this carbon monoxide and the carbon dioxide content should be removed from the product gas, the hydrogen.
Okay.
Okay? Therefore, it may be very widely used, very extensively used technology, but it needs further development. Okay? For example, dry reforming may be preferred instead of the steam reforming in order to produce the hydrogen rather than the steam reforming. Okay?
Okay. Thanks for your attendance, Professor R. And our next speaker from Italy, Professor Francesco Cotone. Do you hear
Hello?
me? Hello,
Yes.
Francesco.
Hello. Hello, everybody. Do you hear me?
Yes,
Yeah,
we can
it's
hear
clear.
you.
Thank you.
Do you see me?
Okay.
Okay.
Professor Francesco from University of Perugia, Department of Physics and Geology. And Professor, you can share your presentation, please. We just check.
Yes, I will try. Okay.
Professor's topic is nonlinear electrostatic microsystem for enhanced energy harvesting. Yes,
Do you see my screen?
Yes, we can see.
Okay, very good. Okay. Yes. Okay. Thank you for inviting me to participating to this conference. Even if unfortunately it is virtual, but still very important to participate. So it's a very interesting conference. So my name is Francesco Cottone. I'm from University of Perugia in Italy, and I'm going to talk to you about a very different topic, still on energy, but this topic regards the vibration energy harvesting for powering small devices, small wireless devices, electronic device. So I will talk to you about. First, I will introduce you in this topic and talking about the microscale vibration energy harvesting systems and the applications. And go through the more specific. I will show you more in deep some technologies based on MEMS and electrostatic transduction technique. And then I will show you some recent research on microelectronics materials that can be embedded and integrated with vibration energy harvesting systems. And I will talk you also on recent development and on recent and the big potential of 3D printed devices, which are quite interesting before of the low cost of manufacturing and the fast prototyping. And then I will conclude this talk with some remarks and perspectives for the future. Okay, first of all, microscale energy harvesters. Which are the main applications? All you know about the big trend in the expansion of Internet of Things. All the wireless, small and medium devices that are around all the world and are becoming more and more pervasive. And these devices are wireless and need to be powered by some source of energy. Commercially, most of the commercial devices are powered by batteries, but we want to attack this problem of the energy autonomy by implementing energy harvesting systems. Energy harvesting systems are the systems that get or capture energy from the ambient and convert this energy into electricity to power or to complement batteries of small wireless electronic devices. And at micro scale, why it is important to miniaturize the energy harvesting systems? Because we need to power and to make self-powering some devices, for example, for healthcare, for the monitoring of the body, or even for some actuators like micro robots that can be very useful inside the body to monitor some parameters or to just to make some actions. So we need, for example, one of the main examples are the pacemaker powering. You know that every 10 years the patient need a surgery in order to substitute the battery inside the pacemaker. This is very stressful, and so we would like to have a powering source that can be perpetual, so without the need of maintenance and the substitution of batteries. So this is very important. And also for all the other applications of Internet of Things, these applications cover, for example, agriculture monitoring, military application, infrastructures like monitoring of bridges and buildings and so on. So the power required for small, medium devices that are wireless now is in the range between 100 nanowatts up to 100 milliwatts on average, of course, and we can go also up to some watt or something around watts. But for small devices, this is the main and common range of power that are required. So we need to develop an integrated system in which we have an energy harvester. This is this block. In particular, I will show you about the vibration energy harvesting. So about the systems that converts kinetic energy from mechanical vibrations into electricity. Then the energy harvester will be interfaces to electronic interface, will be connected to an electronic interface to the wireless sensor node, for example, so the device that uses the energy. And we need also a temporary storage system, because since the energy is very variable in time and inconsistent, sometimes variable in intensity and also in frequency. So we need to capture all the energy that comes in and store it temporarily in a storage system. So the storage could be a battery, but now the trend is to find to use supercapacitors as alternative to batteries, because the amount of energy that is temporarily stored is not so high. So, and we need a very reliable system that can be charged and discharged many times. So with a lot of energy cycles. So supercapacitors are a better choice in this case. Then, of course, from the energy that is captured is converted, part of it into electricity and part of it is dissipated into wasted heat. So there is also a certain amount of energy that is dissipated and a certain amount of energy that is dissipated through wireless connection, so electromagnetic radiation. Okay. All these devices can be connected to a cloud in order to collect all the data that comes from this, for example, a wireless sensor network. And this is very important. This here in this slide, I will show you some of the early examples of small vibration energy harvester. In this case, it is since 2005. This is a piezoelectric vibration energy harvester. It's very small. It's around less than 1 millimeter square. And this is a piezoelectric cantilever. So by shaking it by mechanical excitation, mechanical vibration, the piezoelectric beam converts mechanical stress into electricity, and then this signal is collected and go through, for example, to temporary storage. This is another example, some zinc oxide nanowires from Georgia Tech, also in 2005. These are all examples of a vibration energy harvester miniaturized that exploits the piezoelectric transduction technique or piezoelectric materials. This is another example. This is also less than around 1 millimeter of length, of linear length. This exploits aluminum nitride as a thin layer of piezoelectric material. And then we have also the current collector, that is an electrode in aluminum and a seismic mass. Another example by 2010 by EPFL. This piezoelectric device uses an interdigitated comb electrodes, for example, in order to use all the electrical field that is generated along all the length of the piezoelectric cantilever. This is made of PZT, for example, or deposited over silicon beam. This is another example of here is a piezoelectric energy harvester mounted over a moth, and so the vibration of this animal generate power, and so this can power, for example, some miniature sensor that can be integrated to the animal, to the fly. So and recently, in 2019, some recent advancements in 3D printed piezoelectric materials. This is from MIT. So they succeeded in synthesizing some ink, piezoelectric ink that can be, or piezoelectric material that can be 3D printed with common 3D printer, for example, FDM, fused deposition modeling systems. And the news here is that this kind of material is actually is quite efficient in the conversion from mechanical to electricity. This is not trivial to obtain. There is a lot of research on this at the moment, and there is big potential. In this slide, I will show you some other examples instead of different kind of transduction method for vibration energy harvester. Here is from Paul Mitchison in UK. Is an electrostatic planar capacitor that converts vibration. So by changing capacitance of the capacitors, convert vibration of the seismic mass on the top into electricity. And this is electromagnetic inductors, the miniature electromagnetic inductors, so made by some coil and a seismic mass suspended by a spiral springs. On the bottom, we have another examples of electrostatic comb vibration energy harvester, and on the right, this is a device that I had developed at ASIE Paris with the Professor Philippe Basset. This is based on silicon, so this is this has been manufactured by deep reactive ion etching on silicon, and the area is about 1 centimeter by 1 centimeter, and 1 centimeter by 1 centimeter, and this is quite efficient at low frequency. I will show you more details about this. And then on the bottom, we have another example of miniature inductive vibration energy harvester, made also with a sort of nonlinear spring structure, made of spiral spring with very, very compliant springs, and seismic mass and electroplated copper coils on the bottom. So, but what is the main challenge of miniaturizing vibration energy harvester? So the problem is that the ambient vibrational sources are, most of them, located at low frequencies. So which means that if we look at the power frequency spectrum, most of the energy is below a few hundred of hertz. So which means that we need to design our vibration energy harvester in order to be efficient at low frequency. So let's say from few hertz up to 100 hertz or 300 hertz. So most of them are below few hundred hertz. Which means that this is a problem, because if we miniaturize this in this slide, you see some example. For example, vibration spectrum from train, a microwave oven, so household, a working person. As you can see here, we are well below 10 hertz. A working person, typically, most of the energy of is located around 2 hertz, something like that. Then we have some bridges, but also in the bridge, this is the Chicago North Bridge, for example, you see that is below 50 hertz. The main peaks are located here in the car, for a car in a highway, for example, near 20 hertz, and another one is near 2 hertz. So, and I want to also stress this link that that offers a database of many vibrational sources that can be used by researchers. If you are interested, it is for free. You can get access through this link and download vibrational sources in order for you to make some experiment, for example, or simulation in the lab. Then I will provide you more details about this in the following. So as I was saying, one of the big issue is the scaling issue. So by reducing the dimension, the size of a vibration energy harvester, what we do, we increase the natural vibration frequency of the harvester. At the same time, we reduce the power, but also we reduce the seismic mass. So we increase the vibration frequency, the natural vibration frequency that goes well far from, so that becomes very high. And so there is a mismatch between the natural frequency of the vibration harvester and the natural ambient frequencies, that is the source. So, and another problem is that most of the vibrational energy harvesters are based on linear oscillator system. So a linear oscillator, as you know, present a very peak, very high energy peak in correspondence to the resonance. But if we go a little bit far from the resonance, we have very low efficiency in the transmission of the vibrational energy from the source to the device. So we have low efficiency of resonance, high resonant frequency at miniature scales. And if we make some simple calculation, for example, taking for instance, vibration energy harvested based on piezoelectric cantilever, we see that the power is proportional to the square of the acceleration, input acceleration, and goes to the power of 4, the fourth power of the linear length or linear dimension. If we consider, for example, the oscillator as a cube, goes as the fourth power of the linear dimension of this cube. Which means that if we plot, for example, here is a logarithmic scale. If we plot the power that can be generated by a vibration energy harvester as a function of the length or of the linear length, and we plot also the natural resonant frequency of this vibration harvester, we can see that the power, of course, decreases very fast. And this is a logarithmic scale. So by going from a length that includes all the MEMS scale, for example, down to the NEMS scale, so nano electromechanical system length, we see that we get very low power. So 10 to -10 and so on. So this is a big problem, of course, but at the same time, we need to think about decreasing at the same time also the power need of the device. So if we consider, for example, a tiny sensor of temperature sensor, it is possible to reduce the power consumption of this sensor down to nanowatts. So recent advancement in reducing the power consumption of miniature sensor based on CMOS technology, for example, helps this research in matching the power that can be provided by vibration energy harvester. On the right, you see the plot of resonant frequency as a function of length. The problem here is that, again, the resonant frequency of a system, for example, based on oscillator, goes high, very, very high. So from MEMS to NEMS, and this decreases, of course, the efficiency. Now I will show you more in deep an example of a device that we have developed in collaboration with the ISI Paris. And this device is the one that has been presented previously. It's based on a deep reactive ion etching, and it is a capacitive comb interdigitated comb vibration energy harvester made of silicon, attached over a glass and a glass cover. And this has been also charged with so we implemented also electrodes on it in order to provide a constant electrical bias to this capacitor. Because I don't know if you are familiar with capacitive vibration energy harvester, but one of the big problem of this harvester is that we need to provide a pre-charge to the system by giving a bias voltage at the beginning in order to charge it. And we have to keep this bias voltage. So normally researchers use an external power source, then that is subsequently recharged by the system itself. But this is a problem. So we need, if we want something that is totally passive, so that we don't have to provide the additional power to it in order to operate, we need to implement electrodes. So electrodes materials are materials, usually dielectric materials that can be charged permanently, like magnets, with the static charges. Okay, so with the corona discharge, so we fabricated a device. This is the scheme in the A figure, the scheme of the comb interdigitated finger vibration harvesters. And as you can see here, you can see the serpentine springs that connect a moving inertial mass to the static part of the system. So by moving the inertial mass, we change the distance between the fingers of this comb capacitor. So we change the capacitance, and by changing the capacitance, we generate electricity. We generate a movement between charges of the two electrodes. Here it is a photograph of the device that is the length is about 10 millimeter by 10 millimeter by 0.5 millimeter of thickness. So actually in thickness is very small, and the number of combs of fingers are around more than 200. And this is connected to FR support. Okay, I will go through very fast about this. I will not provide too much details, but the special characteristic of this system is that inside the seismic mass we put a small microball in titanium microball, and this actually tungsten microball, sorry, and this microball can move freely, and he can hit the boundaries of this cavity. You can see maybe, or even in the picture here. I cannot maybe zoom it, but there is a small microball in it inside the cavity. So why we put this microball inside the cavity of the seismic mass? Because we want to exploit a very low frequency vibrational sources, like, for example, a movement of a hand, of a wrist, of a people. And by moving at very low frequency, the small microball can move freely. So what it does, it hits the boundaries and excite the seismic mass. So this is sometimes called this phenomenon like, sorry, this is called frequency up conversion. So we pump energy from low frequency to high frequency of normal resonance of the system. In addition, you can see here the plot of a potential energy, the effective elastic potential energy of the seismic mass as a function of the mass position. As you can see, by changing the bias voltage, that the bias voltage, so the static voltage different potential difference that is provided to the two electrodes of the comb capacitor, we change the shape of the effective elastic potential well of the system. So we change the dynamics of this oscillator. In particular, you can notice that at the band, at very far from the equilibrium position of the centers, the elastic potential energy starts to show some wells. So these wells is due to the pulling force, the electrostatic pulling force that is generated between the comb, between the electrodes of the comb when they are very close. So these wells implement somehow a nonlinearity of on the dynamics. So the system has now three, not only one equilibrium position, but starts to with high potential bias potential, starts to have high, very high nonlinearity, and starts to be to present three, not only one at the center equilibrium position, but 1, 2, and 3 equilibrium positions. So one at the center and two at the sides. And this provided the system to be more nonlinear, and it becomes more efficient because it is able to get energy from a wider vibrational spectrum. Here, I don't know if it works, but here is a picture of the system in vibration. And this, I'll try to make it starting. This is just a movie, a small movie of the vibration of the electrostatic vibrational energy harvester. As you can see, there is a vibration of the seismic mass and the vibration of the microball. So when microball impact, there is a velocity amplification and also a transfer of kinetic energy from the balls to the seismic silicon mass that normally has a normal excitation frequency of around 160 Hertz, while in this way the system it is capable of getting energy from very low frequency by, for example, vibration at 2 Hertz, 3 Hertz, and around 10, and so on. And so here are some of the results, experimental result. Here you can see the RMS voltage that is generated, provided by the system when doing a sweeping in frequency, when just providing, for example, a sinusoidal signal to the system, a sinusoidal excitation spanning from few hertz up to 120 hertz. As you can see here, the response of the system with and without microball. And you can see there is a power enhancement and a widening of the frequency response of the system. This is very important. Here on the right, you can see the capacitance variation over time that is measured with a fast, with a high bandwidth oscilloscope. And the capacitance, the variation, so the bigger is the variation of the capacitance, the bigger is the energy that is converted from mechanical to electricity. So one of the main objectives designer of capacitive vibration energy harvester is to improve as much as possible the variation of the capacitance. And here also the max power that is generated by varying the bias voltage with and without the microball. Here are some numerical simulations that show you a little bit better the behavior of the system. Here on the left, you can see the displacement of the seismic mass, the black line. The ball displacement that is simulated that hit the two boundaries, the upper and the lower boundary of the cavity, that at each hit, the cavity starts to vibrate and vibrate, so the seismic mass vibrates at its own natural frequency. Here is the vibration of the capacitance and the vibration of the variation of the generated voltage. As you can see also, the results, the simulated results with the microball hitting inside the cavity or without is very clear. So I show you that we have a peak that is due to the natural frequency of the seismic mass, and then we have a lot of energy generated with the impacted microball at frequency below very few hertz, like 0.12 hertz up to 40 hertz, that we don't have in case we don't have the impacting microball. Okay, this is just another zooming of the results, but actually this is what happens also experimentally, but we don't have the possibility experimentally to, or we didn't measure we didn't track the movement of the microball inside the cavity, but we could extract the movement with a fast camera video. So this is our intent in the near future, to try to get more parameters out from the device in experimental conditions. Okay, so this is another slide about simulation by varying the length of the cavity. Because of course, if we vary the length of the cavity, we are varying the time between one hit and the other hit of the ball that bounces up and down or between the two boundaries. So by varying this, we change also the mechanism of the frequency up conversion. So the mechanism behind the energy transfer from low frequency to high frequency. This is very interesting because we can optimize the device for a specific application. For example, if you want to use the device to get energy from human movements, from walking people, or from a heartbeat, for example, in order to power a pacemaker. So we can optimize by changing the cavity length and by changing some other parameters, of course, for example, bias voltage of the device. So for example, here in this plot, you can see the generated power as a function of the cavity length that is normalized by the dimension of the system. So the cavity length can change. If it changes, there is some, this is measured for two cases, one walking and running man. For running man, for example, you can see that there is, for a running man, if the length of the cavity increases, we have an increase in the power. But for walking, we have just a baseline. So, because of course, for a walking people, so which means that the ball continuously hit even at a lower rate, but still provides the same amount of energy that is transferred to the seismic mass. The max power density that is generated reached 15 microwatts, and the power density around 143 microwatt per cubic centimeter. This is the power divided by the volume of the device. So it is a common used parameter to make comparisons between different vibration energy harvesters. Okay. Okay, these are other experiments with the same system, without the microball and with the microball at different acceleration input at 0.5 G and at 2 G on the bottom. As you can see, of course, with higher acceleration input of vibration, we have higher power, generated power. And the power also, the blue and the red refers to different bias voltage. Actually, this bias voltage is provided by the implementation of electrets. So we deposited on the system on silicon, we deposited a small layer of a coating of parilene, and that parilene was charged by corona discharge. And this, depending on the energy of the corona applied to corona discharge method, we obtained 46 volts of surface constant potential and 21 volts with two different experiments. And this is quite high, actually, potential that is provided by electrets at the surface, and this potential pre-charge automatically the system. So the system doesn't need to be pre-charged by an external bias voltage. So it's totally autonomous. As you can see, with the microball, we have lots of energy also shaken by hand at very low frequency, around 4 and 6 hertz. So and we have a widening on the power spectrum. This is very interesting. Compare, for example, at low acceleration at 0.5 G RMS, you see that there is a big difference in the presence of the microball inside heating or without it. This is another test did by hand shaking, and by hand shaking we charged a small capacitor, a 47 microfarad capacitor has been charged, and this capacitor through a bridge diode rectifier, and this capacitor provided 3.5 volts to supply a wireless temperature sensor node. So the system shaken by hand is capable to provide enough energy to power a small sensor like a temperature sensor node that is also wireless. Okay, this is just a comparison with other similar devices, similar generators, and our generator actually shown a very high power density, as I said before, so more than 142 microwatts per cubic centimeter, which is quite remarkable. Recently, there are also different, of course, there are many kind of vibration energy harvester based, for example, not in capacity on the capacitive transduction, but based on, for example, inductive or piezo. But inductive systems are not very suitable for miniaturization still, below 1 centimeter. Piezoelectric also needs to be improved, also for the cost and the deposition of the piezoelectric material and so on. Okay, now this is just another improvement that is ongoing about this device is implementing the pull-in free effect. The pull-in free, you know, when the two plates are very close, as I said before, we have the pull-in force that make them sticking together. So in order to avoid this, we are just exploring some other configuration of the capacitor in order to avoid the stiction. So, and to do this, we are thinking in implementing some repulsive electrostatic force in the device that equilibrates the attractive one. So a configuration like this one, as you can see here, in which we have some separated electrodes by a gap, and close to the seismic mass, this provides some repulsive electrostatic force to the system that can equilibrate. And by changing the voltage bias, we can change the electrostatic force from negative to positive, as you can see here in the second plot on your right. So this is another research that is ongoing. We still don't, these are just preliminary results, but it's quite promising. But in principle, it can, this can avoid stiction of the combs in this type of device, in this type of generators. Another research that we are carrying on that is related to the electrostatic vibration energy harvester is research about materials, electret materials that can be embedded or integrated with the system, with the generators. One material that is quite interesting is silica or silicon dioxide microspheres that can be found also commercially. You can buy wherever, also by Sigma Aldrich. And these materials, the silica is a very nice materials suitable for to be an electret to store static charges. And what we have done, we studied and investigated these microspheres that is of the size of 1 micron each of diameter. And these spheres have been charged with the SEM, scanning electron microscope, directly inside the SEM, but just by changing and varying the energy of the electron beam. So for example, here you can see some pictures at 8 kilo electron volts or 3 kilo electron volts. By varying the electron beam energy, you can inject charges inside the silica particle up to a depth of 209 nanometer, for example, 200, 300. And by varying the energy, you can charge both positively or negatively. So this depends on an effect of surface effect in the impact of the electrons. So they can be emit secondary electron inside and can just extract atoms or electrons inside the microsphere. And so you can charge the spheres negatively or positively, but most of all negatively. So you can inject the negative charges on it. And the charge concentration that we reached is around 0.1 coulomb per see, this is centimeter cube, sorry, this is not meter cube, but centimeter cube. So it's 0.1 coulomb by centimeter cube. Then our aim is also to embed these particles inside the electrostatic capacitor, electrostatic device that is, for example, can be this one here on silicon, or even to use these charged particles inside a polymer matrix as a filler that can be also 3D printed, for example. So we did some experiment of by fabricating, for example, PLA 3D printed comb electrostatic vibration energy harvester like this one. Okay, this is just a first very simple prototype in which you have 2 electrodes, so 1 and 2. Actually, these 2 were then electroplated with copper. So in order to make them electrically conductive, but also you can find some materials that are already, for example, conductive, like PLA, conductive PLA, or PLA charged with copper nanotubes that you can find also on the market in order to print out directly a conductive materials. But we did some tests and we found that the electrical resistivity is not very low actually of commercial materials. So it's better to make an electroplating of plastic after the fabrication is much better. Here below, you see some other example of small cantilevers that can be have been printed with the SLA stereolithography 3D printers with resins. In this case, it is a clear resin. What is interesting is that even if we don't reach the minimal feature that can be reached by deep reactive ion etching, for example, on silicon, but we reach a very, very nice device. We achieved to make very small devices, very small cantilevers below 1 millimeter by 1 millimeter of length and of 0.1 millimeter of thickness. Actually, we reached 0.05, so 50 microns of thickness for this kind of cantilevers. Then this will be electroplated and will be charged with a coronal discharge. So we are doing research on this. The big advantage of 3D printing is that you have a rapid, very rapid and very low cost prototyping compared to the manufacturing of devices in a clean room, for example, with the normal techniques of etching or deep reactive ion etching or CVD or so on. So by using 3D printing and electroplating, that are two very, very low cost techniques, actually today, nowadays, it is possible to make very nice and effective vibration energy harvester. So micro generators actually of below 10 millimeters and below also 1 millimeter of length. Okay, I'm almost done. Well, I want to just show you and provide some advertise of this project. This is the project that we that also funded all the research that is ongoing. Is the project called Enables. This is an European project that provides you free of charge rapid access to facilities of this consortium. So this consortium provides free of charge access to the facilities to make research on energy harvesting, energy storage, and micropower management. And it is open to all Europe, but also outside Europe. So if you want to have access, just go to this link, enablesproject.eu, and make us a free registration. So you can provide a small proposal to make, for example, a feasibility study or something that you need, for example, about the design of an energy harvester. And we have the money, so the consortium has the money to pay you to stay, for example, 2-3 days, 1 week to do your research. So this is a platform to enable research on powering the Internet of Things, so energy harvesting, energy storage, and also power management. So energy storage, so which means that if you have to do some research on materials for energy storage, for example, for batteries or supercap or energy harvesting systems, you can go, mostly researchers and students or PhD students can just make a subscription and exploit. On the top right, there is a link of our, as I said, vibration energy harvesting database that you can use also for free. You can download all the type of vibration signals and use it for your experiments. So I've concluded. So nonlinear MEMS has been demonstrated to be very, very good also at low frequency and provide wide bandwidth energy harvesting. We show also an interesting configuration with impacting microball that can be useful to to make energy pumping from low frequency to high frequency, and so in order to capture energy, improve the capturing of the energy at low frequency, for example, from human movement. We show that this MEMS Mason silicon shown a very high power density, and I provide you some insight about also about also microelectret materials like microsilica particles that can be used to provide very high level of charges, and can be used also integrated to polymer or matrix or in general in electrostatic vibration energy harvesting systems. And then I'll show you also some recent advancement in 3D printed techniques, and the 3D printed techniques show a very big potential for a low-cost prototyping and manufacturing that is alternative to classical MEMS fabrication. So this is very important also in order to transfer this technology to real world, to the industry, and to the market. So we are very looking forward to improve our research on this field. So I've concluded, and I'd like to thank you, all the staff, all the organizers of this conference, and I'm here also. This is a picture of Perugia. Unfortunately, due to COVID, we don't have many visitors at the moment, but I would like to invite you for the future to visit our beautiful city. So I'm concluded. Thank you.
Thanks for your presentation, Dr. Francesco. Yes, audience, do you have any questions?
Just thank you. It's a very great presentation.
Thank you.
Okay, thanks. Dr. Francesco, I have one question. Actually,
Yeah.
you mentioned that change the capacitance, your system produce electricity. Am I right?
Yes.
Yes.
Exactly.
But the power density, what it is low actually. Others, when you compare the other systems, the maximum you mentioned that 140 or 30.
Yes. Per cubic centimeter.
Yes. When you compare the small battery, what would you say the advantage of this system? Maybe in the future sensor technology, it is possible to use this kind of material, or maybe to make a hybrid system. It is possible. Yes,
of course. Yes. First of all, we have to distinct the two technologies. So a battery has a certain amount of energy that can be used for a certain time. So if you, for example, imagine one lithium battery to power, for example, a pacemaker for 10 years, for example, the power density that a lithium battery provides for 10 years for a pacemaker is below 150 microwatts per cubic centimeter. So which means that actually with this kind of generator, you can provide the same amount of power density of the battery for more than 10 years, so continuously. If when you have a continuous or source of vibration from the ambient, you can continuously and perpetually power the device. So this is the big difference. So it depends on a battery needs to be recharged, can provide a high amount of power in a short time, of course, much higher than the power density of this generator, but in a short time. Instead, the generator can provide a continuous power for very, very long time. Let's say the time that it can survive. So the mechanical system.
Yeah.
But of course, it can be integrated to make an hybrid system. So generator, as I shown in the early slides, needs always a small storage system that is temporary storage, because the variation of the energy source.
Okay, because yes, as very impressive technique actually. Because we are also trying to construct a microbial MEMS-based cell. Okay, it is we are using some bacteria to produce some energy, but your system very effective when we compare our system. Okay, but how about stability? Is it stable for the long time? Dr. Francesco? I think the line is problem now. Okay, Dr. Francisco, there's a problem for the link. Okay, yes, audience, we are now waiting for the next speaker. We have now break for the 15 minutes. If we here, okay, we can start 12:30. Now we have a break now.
Uğur hocam,
Ne olmuş, gelmiş mi?
şey bitmiş herhalde de hocam.
Öyle
Bir saniye.
gitmedi. Ben dedim kapat. Siz
Gelen-
Yok, hayır Uğur hocam burada. Şey bitmiş.
Gelen yok herhalde arkadaşlar, değil mi şimdi?
Yok
Evet Sayın
hocam.
Hocam. Hocam kapanışınızı yapın.
Hakan hocamla o zaman kapanışı yapayım isterseniz. Hakan hocamla konuşayım mı isterseniz? Çünkü bundan sonra bir gelecek daha vardı ama o gelecek mi bilmiyorum ama.
Hocam bir konuşun isterseniz siz Hakan hocam.
Bir konuşayım, ondan sonra yap. Now, I am closing this section. Thanks for your attention. Arkadaşlar çıkıyorum ben de.